So much for being here. Thank you, Dennis, for the introduction. Awesome. So the topic of our talk today is Lagrange and the unique approach that Lagrange takes to ZK coprocessing. So to start with, I hope some people here are familiar with ZK coprocessing. It's been talked a lot about on Twitter, but for the purpose of this talk, we're going to assume no familiarity. What is a ZK coprocessor? The simplest way to think of it is as a scalability solution. A scalability solution not in the form of a new blockchain or a new way to horizontally scale execution like a rollup, but a scalability solution in the form of something that lets you take your existing smart contracts deployed on your existing execution spaces and to scale the computation that they can access. And we do this through verifiable, in the form of ZK, off-chain compute. In particular, what we focus on is ZK coprocessing in the form of letting you prove SQL or SQL computation over historical transaction storage and receipt data directly from your smart contract. So your smart contract can ask SQL queries of the blockchain that it runs on. For example, select all transactions from users over the last 90 days. What is the TWAP of a curve pool on my chain so I can price some collateral directly from your contract. Now, the way we do this is through a decentralized set of provers that run off-chain on eigenlayer that generate proofs. Each of these provers has a stake, and in the event that they don't deliver a proof back within their requisite time slot, they face an economic sanction. We have deployed on mainnet very recently with a number of marquee operators, including Coinbase, OKX, Kraken, AltLayer, P2P, etc., that are live computing proofs in production today for our infrastructure. We serve approximately 10,000 queries a week for smart contracts on Ethereum and Ethereum-compatible L2s, and we generate about 420,000 proofs per week, and that's actually not a joke. And so the core of how this works is through our decentralized network that stratifies work across two sets of protocol participants. The first being gateways, the second being provers. So provers can be thought of as workers whose responsibility it is to generate proofs for end users who request work from a gateway. A gateway takes a request, for example, moving average of price on some series of contracts over some range, breaks that down into a query plan. If anyone here is familiar with databases and you can think of how query plans are structured over databases, think of the gateway as the same abstraction. And then it assigns that work out to the provers who, in a parallelizable fashion, generate proofs that are recursively combined back together and delivered back to your smart contract on-chain. And so in line with this flow, if you want to leverage this today, you deploy a contract that inherits our interface. You can specify in SQL the type of query you want to run over the relevant section of blockchain data you want to run it on. And then you request that proof from a gateway. The gateway handles the assignment, the orchestration, and then the eventual returning of that work. And provers generate proofs within this network for a fee. So how do we do this? And what is the scale of the compute that you can typically do? Why would I want to use a ZK coprocessor? What does scale even mean in terms of being able to read from on-chain data? So if anyone here is familiar with Solidity engineering, you likely know that reading a storage slot is about 2,000 gas. So if you want to, for example, determine all users who have a pudgy penguin that matches a certain metadata property, and you want to iterate through the entire list of pudgy penguin, the entire mapping of pudgy penguin holders, about, let's say, 9,000 storage slots, well, your gas cost is about 18 million. So that's obviously not going to fit in your block limit. That's obviously not very viable to run. So you can't really ask a simple question of like, okay, who has a pudgy penguin that has a fish on its head? You can't ask a question, for example, of, well, who has held a pudgy penguin over the last 90 days? My application wants to issue some reward to that person if they continue to hold that every block. You generally you can read this data off-chain, but you can't, from your contract, actually access that data the same way that you would typically do if you could structure computation in a Web 2 context. And so we let you ask this. We let you have these types of questions that can be proven with zero knowledge from our network back on chain. And so we do this through a novel approach that we call verifiable SQL through decomposition. So hopefully some people here are familiar with ZK VMs, right? General purpose machines that can prove, let's say, Rust computation for an arbitrary program. We focus on a new approach, which you can almost think of like a ZK VM for SQL. You specify an SQL query. We can parse that query into AST tree or abstract syntax tree operations that would run over the data. And then we can map that, or we can project that in a MapReduce format on top of data that we can prove using our network. So you can see a very simple example here of a select query that we break out into a create, range, project, sort, and then an arithmetic operation. And then we can prove these in parallel across our network. And why this matters is that you can now structure this computation over on-chain data in ways that were historically non-verifiable and couldn't be consumed by your contract. It means you can take applications that sit on Ethereum today, you can take your lending apps, you can take your DeFi apps, and you can add new features on top of them. You can have your DeFi apps issue rewards for users, issue discounts, etc. And so the way this works typically is through two phases. We require users to specify their data frame that they care about. They specify their database directly from their contract. And we can provably build this database through generating proofs of the correctness of indexing blockchain data continuously. Then, when you want to query that, you emit an event from your contract, and we return back a proof of the computation over that state. And so we have a lot of research that our team does, thanks to Babis and Travon, a number of our cryptography researchers, that makes this verifiable indexing a lot faster than the prior state of the art. So to put this in perspective, we can structure proofs of computation over about 1 million storage slots in asymptotically about 30 seconds, and in practice about 1 minute 20 seconds. Which means if you were to think of the gas cost of 2,000 gas times 1 million storage slots, right, you're going to talk about 2 billion gas. You're not at no point ever going to be able to structure that type of read operation over data in your contract, let alone the computation you want to run over that. We can do this today in a proof in about 1 minute 20 seconds, which means that your contract can actually leverage this data in a trustless fashion directly in its execution logic. And so we can do this over storage data, receipt data, transaction data, etc. So first you define your database. We pre-process that by generating a provable indexed version of this data. And then we let you structure queries over top of that. And these queries, as I specified before, can be structured in basic SQL syntax. So it means that however you'd think about interacting with data in Dune Analytics, for example, or Nansen, or any of these tools that you would traditionally look at off-chain for thinking about relationships with blockchain data, your contract can now leverage very similar logic to verify the results of those types of queries over the same blockchain data sets. And so to look at the developer flow, we have, as a group, worked to make this as ergonomic and easy to use as possible. So, as I mentioned, the first step is specifying the data that you want to be provably indexed. The second step is specifying a query over top of that data that has been provably indexed. And so, to do this, you register a contract with our prover network, our gateway. Our gateway is responsible for looking for emitted events that match the specific schema and iteratively building verifiable databases that are provably indexed on top of the specified data. So you can say, I want this mapping, I want these storage slots in my contract, I want these events, I want this block range, this is how I want my data set to look. And then our network provably builds these databases. And I keep saying the point provable because that's very important for understanding why this has a high degree of underlying security. When the network returns back to you a proof of a computation, you're not trusting the network. You're not trusting some series of nodes. You're not trusting me. You're not trusting my team. All you're trusting is mathematics. You're trusting that the proof that you've requested can verify on your contract. The verifier is in the contract that before you interpret the data and use the data, has to verify. Next, you inherit our query interface, where you specify the type of query that you want to run. You define off-chain the SQL statement, and then you have a compiled verifier that can be used on-chain to verify it. And so you make a call to us to specify the type of query you want to run, and then you specify a callback address that, once the proof is generated and the data is returned, can be used to interpret and use the result of this query. So the first version that we launched earlier this year, we call Euclid several months ago, and this focuses on queries over ERC20 and ERC721 data, over mappings. The reason we did this is because we wanted to prove that we can handle scale. We can handle scale of 1 million storage slots. And soon we'll be able to handle scale in the range of 8 to 9 figures worth of storage slots, which is a massive amount of data that your contract could otherwise not actually compute over or interpret results that are generated on top of. And so once again, you process your callback, you get back a tuple of the results. Obviously, there's gas limits over call data, so you have to restrict the amount you want, use limit statements, et cetera, the same way you would in SQL if you were handling a query over an API. And then you get your request ID back, and you can ensure that, and you can verify that the data you got back is correct, since the verifier contract has successfully run and has successfully checked out that the proof is correct. Now, this is a very large topology of how our network currently works in the production context. The beauty of this type of design is the computation you run can work in both single chain and cross-chain contexts. The final verification input to your proof is simply the block header of that chain. And so any Solidity developer here knows you can access block headers of the chain you're currently on with a block.header call. And if you're building on an L2, you can typically access block headers. Let's say if it's an optimistic rollup or an OP rollup, you can access that through a pre-deploy, letting you access L1 routes. And if, for example, you're now on some exotic execution space with some exotic settlement logic that doesn't have access to doesn't have access to the block header of Ethereum or a block header of another chain you want, you can use an arbitrary cross-chain protocol. You can use something like Axeler, something like Layer 0, something like Wormhole to move the block header that you want from source chain to destination chain. And then the computation that we offer and the proof of the computation that we offer inherits security from the block header that was moved. Because you can think of this as a way to set an abstraction on top of the inheritance of security. So this flow, very simple. You register a contract, you send a query to our network. We're thinking of this in a single chain context, for example, where blockchain 1 and 2 are the same chain. And then we verify a proof and send the result back. The network is responsible for generating that verifiable database, for serving computation back, where individual prover nodes, the ones I've mentioned, the ones that are run by teams like Coinbase, Kraken, OKX, are responsible for generating these proofs iteratively over this data. And there's some very interesting properties that our team has within our constructions that I don't want to bore the audience here with, but one of these is updatability, which is something that you've historically not had access to in zero-knowledge proofs, wherein if you generate a proof of some computation and then you change some parameter within the public statement or the witness, you have to regenerate that entire proof of computation from scratch. Obviously, when we're talking about queries over data sets or indexing over data sets, the amount of reused computation is very high, right? So if I build a data set between block B and B plus K, and now I want to build it between B and B plus K plus 1, I don't want to have to regenerate my whole indexing proof. And so the reason that we can keep our costs low and we can, in fact, do this is because of a new line of work called dynamic snarks that our team has pioneered. So for those of you who have a research background or an inclination to learn more, please check out some of our work, our RECL trees paper, and very soon our Perseus paper 2 will be out. And so to talk a little bit about Lagrange as a company, hopefully I haven't bored everyone here out of the room. So we have generated over 1.8 million proofs, should be about 2 million proofs very soon in our network. We've served 83K queries across 4 chains, Frax, Base, Mantle, and Ethereum. We've generated a number of state proofs on our network as well, and we're integrated with over 50 projects currently, and we have over 50 operators running our provers. And so now I really kind of want to make this concrete by talking about a few use cases of where developers are and will be leveraging our computational primitives within their core DeFi logic. So one of the common use cases within DeFi protocols is reward-bearing contracts. Some of you might be familiar with these in the context of points programs like EtherFi does, or you might be familiar with these in the form of sushi MasterChef contracts, like a lot of popular DeFi protocols use. The basic premise is very simple. You hold a yield-bearing token, and every single block, you receive a reward that's proportionate to the total supply that you hold. This is great. This can be instantiated off-chain and read on-chain, but then you have to trust the party who's writing back your data, and it's very hard to structure claim logic on a bunch of Merkle tree payout claims. Or you can deploy a specific standard, like a sushi MasterChef standard, but you face limitations with that over the ability to structure multiple payout pools and the ability to run these types of rewards programs over existing tokens. Right? You have to deploy a custom contract to record basically the accumulated payout at any point in time, then try to go back and pull a storage slot from a previous point, and the logic gets very, very messy. Obviously, if I asked anybody here with a computer science background, hey, here's a database, write a SQL query to define the statement, very, very, very simple. So this is the type of thing that you can do with the coprocessor. And so we work with a lot of teams on this that we're quite excited about very soon announcing more. Now, another interesting one, and this is one that, I don't know who here is an NFT fan. I know NFTs have not performed well as an asset class recently, but hopefully I think they're going to rebound. But we're very bullish as a group on NFTs and on kind of the interesting dynamics you can leverage on top of these when you have expressive computation coupled with NFTs. And so one of the common things and the common threads we've seen from NFT protocols is to want to build on-chain experiences for NFT project users that, in fact, leverage the underlying NFT asset ownership as some component of that experience. To put that concretely, if you held my NFT since Genesis, I want you to get a special reward in some on-chain game that I built. I want to issue you a badge that you can claim at any point. I want to give you some reward, maybe a discount on swapping my native token on my new game I'm building if you have met some condition of on-chain actions while also holding my NFT. Once again, if I put all of those transactions and all the receipts and all the storage slots in a database, I could very easily ask you, hey, write a SQL query to prove this, or to get this data. But your contract, if you're trying to think of how you structure that logic on Solidity, gets very messy, right? You are not working in Solidity with a language that is suited or designed for large-scale computation of our data, right? You're on a blockchain that generates massive amounts of data and is fundamentally a versioned, authenticated data structure, but you're working with a language in the execution client that's meant to define contracts and interact with the current state. So this is the type of thing that you can now prove with our coprocessor. You can leverage the proofs in your contract and start underwriting and giving out any type of incentive or reward to end users with a very, very low lift in terms of developer experience. And so for those of you who want to learn more or get in early in terms of building with our primitives, or who just want to join our Discord and maybe play around and hopefully learn something new, well, please scan this QR code. As I mentioned before, we have our prover network that generates these proofs in production right now, and we have launched the first version open source on our GitHub for those who want to check out how this works in practice. And we have a very, very big launch coming in about 4 or 5 weeks that will be the first time in the blockchain space, or actually in any space, where you can run what you can think of as our SQL zkVM, where you can specify an arbitrary SQL query, and we can parse it into a custom circuit and can prove the computation over the inputted data.